Inside almost every single smart device you use, your phone, your watch, even your car's infotainment system, there's this unsung hero quietly doing its job. It's not the fastest part, it's definitely not the flashiest, but without it, things just wouldn't work. Today, we're going to pull back the curtain on the ARM APB Advanced Peripheral Bus, or APB. It really is the quiet, reliable workhorse of modern chip design. So, here's our game plan. First, we'll cover what APB actually is. Then we'll look at the simple handshake that makes it all work. After that, we'll see how it's evolved over the years, check out some of the smarter and safer features it has now, and finally, we'll get to the heart of why this simple protocol is still so incredibly important today.
All right, let's dive right in. First things first, what is the Advanced Peripheral Bus?
Well, if you look at the official AMBA spec, it literally calls it a low-cost interface optimized for minimal power and complexity. And that right there, that tells you everything. The whole mission of APB isn't about blazing speed. It's about being simple, power efficient, and super easy for engineers to work with. So what that means is it's the bus you use for all the low-speed stuff on a chip. Things like setting a timer, managing interrupts, or just flipping a configuration bit. Here's a great way to think about it. If a high-performance bus like AXI is the massive multi-lane superhighway of the chip, moving huge amounts of data really fast, then APB is like the network of simple, paved side streets. It gets you to all the local spots. You don't need a freeway just to turn on a light, right? Same idea.
Now, in any APB transaction, you've got two main players. There's the requester, which, as the name suggests, kicks things off. It's usually a bridge from one of those faster bus systems. And then you have the completer. That's the peripheral device itself, which just responds to the request. The spec used to call these master and slave, but this new terminology is just way more descriptive. It's a really simple, direct relationship.
Okay, so that's the what and the why. Now let's get into the how. We're going to look at the core of any APB transfer, and it all comes down to this really elegant two-cycle handshake. So every single APB transfer follows this simple three-state rhythm. The bus just hangs out in the idle state. When a transfer needs to happen, it jumps to the setup state for one and only one clock cycle. During that cycle, the requester puts the address on the bus, basically saying, hey, I need to talk to you. Then it immediately moves to the access state. Here, a signal called P-enable goes high, and that's the green light. The data gets transferred right then and there. It's super clean, predictable, and totally straightforward. So how does the bus know whether to read or write data? This is the beautiful part. It's all controlled by one single signal, P-write. If P-write is high, it's a write, meaning the requester is sending data out. If P-write is low, it's a read, and the completer sends data back. Everything else, selecting the peripheral, signaling the access phase, it all works the exact same way for both. One little bit controls the entire direction of the data flow. So simple. Of course, the world of chip design never sits still. APB's main strength is its simplicity, but it couldn't just stay the same forever. It had to evolve. So let's take a look at how APB grew up to handle the challenges of more and more complex systems. This timeline really tells the whole story. It all started with APB2, the original super minimalist protocol. Then APB3 came along, adding wait states for peripherals that might be a little slow and a way to report errors. APB4 was a big one. It brought in security with transaction protection and more granular control with write strobes. And the latest, APB5, added stuff for modern low-power design and safety-critical systems. What's so cool here is how each new signal solved a very real problem for engineers. Like, what if your peripheral needs an extra moment to get data ready? Well, Pretty basically lets it raise its hand and say, hold on, I'm not ready yet. Or what happens if something goes wrong? PSVR lets the peripheral yell, hey, that transfer failed. As systems got more complex, security became a huge deal. So pprot came along to enforce access rules. And PSTRB, that lets you update just one byte in a register instead of the whole thing. Super efficient. So this evolution has turned APB from just a simple bus into something much more capable. Let's zoom in on a couple of these smarter, safer features that are absolutely essential for the devices we use today. Okay, let's really dig into that pprot signal from APB4. It's just a 3-bit signal, but wow, it packs a punch. It can flag a transfer as privileged, which is critical for operating systems. It can also mark an access as secure or non-secure. That's a cornerstone for security tech like ARM Trust Zone. It even gives a hint about whether the access is for data or an instruction. This is how a simple bus becomes a key player in a complex, secure system.
And speaking of things going wrong, let's go back to that error signal, PSLVRR. It sounds simple, right? It just flags an error. But the spec has this super important warning. If a write transfer gets an error, you can't just assume the write didn't happen. That register you were trying to write to, it might have been updated anyway. This is a massive gotcha that hardware and software designers have to account for.
So we have a way to handle errors in logic. But what about physical errors? I mean, in the real world, especially in a noisy environment like a car, it's totally possible for electrical noise to just randomly flip a bit from a 0 to a 1 while it's on the wire. How do you protect against that?
And the answer came with APB5, parity protection. This is basically a hardware-level fact checker. The sender adds an extra bit, a parity bit, that's calculated from the data. The receiver does the same math on the data it gets and checks if the parity bit matches. If it doesn't, it knows something got corrupted in transit. For safety-critical systems where one wrong bit could be disastrous, this kind of check is absolutely non-negotiable.
So after all these upgrades and all these years, we get to the really big question. In an industry that is obsessed with going faster and faster, why is this simple, kind of slow protocol still everywhere? Let's break down why APB endures. To really get why ABB is still so popular, you have to embrace one key fact. It is deliberately not a high-performance bus. It isn't pipelined, which means it fully finishes one transfer before it even thinks about starting the next one. Every single operation takes at least 2 clock cycles. And that, which sounds like a limitation, is actually its greatest strength. See, because it's not chasing speed records, APB can be the absolute best at what it's supposed to do. It uses very little power, which is a huge deal for anything with a battery. Its simplicity makes it way easier for engineers to design and test, and because simple logic takes up less physical space on a chip, it's incredibly cheap to add. In the world of engineering, simple, cheap, and reliable is a combination that will never go out of style. And that brings us full circle, right back to the very first sentence in the protocol's official introduction, the sentence that defines its entire reason for being. This isn't some happy accident. It's the whole point. Low cost, low power, low complexity. That's been APB's North Star from the very beginning, and it's why it's still an essential tool for chip designers all over the world. So, I'll leave you with this final thought. The story of APB is just a perfect lesson in engineering. It reminds us that best doesn't always mean fastest. So, think about it. What other simple, reliable technologies are all around us, not in spite of their simplicity, but because of it? Thanks so much for joining me for this explainer.